Hello everyone, welcome to module 10. So in this module we're going to talk about thermodynamics. So on the second part of heat and thermodynamics. So in this lecture we're going to talk about relationships between heat and work, first law of thermodynamics and the second law of thermodynamics. Let's start with the first section, relationship between heat and work. So the objective here is to recognize that a system can absorb or release energy as heat in order for the work to be done on or by the system, and then the work done on or by a system can result in the transfer of energy as heat. Second is to compute the amount of work done during a thermodynamic process, and third is to distinguish between isovolumetric, isothermal, adiabatic, thermodynamic processes. So let's start with heat, work and internal energy. So heat and work are energy transferred to or from a system. So an object never generally will have a heat or a work in it. It only has internal energy. So, but the way it gets transferred is in the form of heat and work. So a system is basically a set of particles or interacting components considered to be a distinct physical entity for the purpose of study. So the environment, the combination of conditions and the influences outside a system can affect the behavior of the system. So in thermodynamic systems, we generally define work in terms of pressure and volume change. So let's see how that works. So we know that work is generally force times displacement. So we know that pressure is force over area. So force can be written as pressure times area. So you can write it as pressure times area times delta x. And now we have area and distance. So which means now you can write area times distance is volume. So from this we can write that work is pressure times change in volume. So here we consider that pressure is constant. So this is work done under constant pressure. So remember this, that we are considering the work done here under constant pressure. Now let's say if the gas expands as shown in the figure and you have a change in the volume. So you're starting with so you're pressing over an area A, applying a pressure P, and you're changing the volume by crossing a distance d. Now we know that here the volume change can be written as V plus delta V. But notice that here there are two chances whether delta V can be positive, where the work is done by the gas on the piston. We can call that positive. Now if the gas is compressed, what happens now is delta V is negative, so which means the change in volume is negative, so the work done by the gas on the piston is going to be negative. So now let's come into the common sense here. So there are two ways we can consider work done. Either it can be done by the system or on the system. So we consider work done by the system to be positive and the work done on the system to be negative. So remember here that the work done by the gas on the piston. So the gas here is the system. So the work done by the system is positive and the work done on the system is negative. So this is how we consider the general considerations. Now when the gas volume remains constant, so we can say that there is no displacement, therefore there is no work done on or by the system. So although the pressure can change during a process, the work done this work is done only if the volume changes. So a situation in where pressure increases and volume remains constant is comparable to E11, in which force does not displace a mass even if the force is increased, so work is not done in either direction. So let's talk about next thermodynamic processes. So we list thermodynamic processes into three types. The first one is an isovolumetric process. Next one is an isothermal process. Third is an isobaric process. And fourth is an adiabatic process. So isovolumetric process says that the change in volume is zero. Isothermal process says that the change in temperature is zero. Isobaric process says that the change in pressure is zero. And adiabatic process says that the change in the heat of the system is zero. So which means here volume is constant. In the second one, temperature is constant. In the third one, pressure is constant. And in the last one, the heat is constant. So these are the four main processes that we generally consider. So if a thermodynamic process takes place at a constant volume, so now considering what is the thermodynamic process here, let's look at each of these processes. If a process occurs at a constant volume, we call that isovolumetric. If it occurs at constant temperature, isothermal, constant pressure, isobaric, and constant heat, adiabatic. So those are the types of work done. So let's come to section 2, the first law of thermodynamics. So the objective here is to first see how the first law of thermodynamics is basically a statement of energy conservation, and we'll try to calculate heat, work, and the change in internal energy by applying the first law of thermodynamics, and finally apply the first law of thermodynamics to apply to cyclic processes. Now, what is energy conservation here? So if friction is taken into account, mechanical energy is generally not conserved. So let's take the example of a roller coaster. So there is a steady decrease in the car's total mechanical energy. It occurs because of the work being done against the friction between the car axles and its bearings, between the car wheels and the coaster track. Now, if the internal energy of the roller coaster and the energy dissipated to the surrounding are taken into account, we can say that the total energy will be constant. Now, notice that here we start with no kinetic energy, no potential energy, and no internal energy. So literally nothing. Now what happens here is that depends on what happens to the system. System is the car here. So there is some work need to be done. That work is to push the energy for a potential energy and the extra work required to overcome the friction, and you reach a certain point. Once you reach this point, you start noticing that you have a high amount of height, which gives you a lot of kinetic potential energy. Now once the cart starts moving, you start noticing that as the potential energy starts decreasing, it converts into kinetic energy, but there is also a loss of energy due to friction, which is generally in the form of internal energy. So the internal energy starts increasing rapidly, and finally you start noticing that the kinetic energy becomes minimum and you have both potential and internal energies. Now the principle of energy conservation that takes into account a system's internal energy is generally called as well as heat and work, is called as the first law of thermodynamics. So the first law of thermodynamics basically states that the change in internal energy is the difference between heat and work. So the change in system's internal energy is the energy transferred to or from the system as heat, and energy transferred to or from the system as work. Now, depending on the signs of Q and W for a system, so whenever you have Q greater than 0, it means that energy is added to the system as heat. When Q is less than 0, we are saying that energy is removed from the system. When Q is equal to 0, there is no transfer of energy as heat. Now, work is positive when the work is done by the system. Work is negative when the work is done on the system, and work is 0 when no work is done. So simply remember that, let's say, we have a simple system right here. So let's say if this is the system. So if the work done here is on the system, this work is negative. If the work is done by the system, we call that positive. Now the energy that is being added to the system becomes positive, and the energy being removed from the system becomes negative. So when the heat is added to the system, it's positive. When the heat is removed from the system, it's negative. So this is the idea behind the signs for Q and W for a given system. So let's solve a simple problem and see how we can understand first law of thermodynamics. So we have a total of 135 joules of work is done on a gaseous refrigerant as it undergoes compression. Now, if the internal energy of the gas increases by 114 joules during the process, what is the total amount of energy transferred as heat? Has energy been added to or removed from the refrigerant as heat? Now, so let's take into consideration the internal energy. The formula is Q minus W. Now, first thing to remember is that it is undergoing a compression. So under compression, we know that work is going to be less than 0 because the work is done on the system. So which means that the work here is negative. So the work done here is given as, there is an increase in if the internal energy increases by 114 joules and the total work done is 135 joules. So they have given us the delta U is 114 joules and the work done is 135 joules. Now work should be less than 0, so which means this is going to be negative. So delta U is equal to Q minus W. So delta U is 114 equals Q minus of minus 135. So 114 equals Q plus 135. Q becomes 114 minus 135. So which can be written as minus 21 joules. So Q is negative 21 joules. So it means that here it says that the heat is being removed from the system. So this is how you can solve the problem. So the Q value is negative, so which means that here the energy is transferred as heat. So you're basically removing heat from the system. So what are the conditions in terms of each processes? So when you have an isovolumetric process, there is no work done, because remember that the change in volume is 0. So P delta V becomes 0, which means the W is equal to 0. So when W is equal to 0, we know the formula is delta U equals Q minus W. So W is 0, so delta U becomes equal to Q. So the change in internal energy is the amount of heat transfer. Next, we have isothermal energies. So in isothermal, we are saying that the change in temperature is 0. If there is no change in temperature, the change in internal energy is 0. So from the formula, we can write that Q minus W equals 0. So which means Q equals W. So the change in work, the change in heat, the energy transfer is equal to the heat transfer. The work done is the heat transfer. Next, we have adiabatic systems. In adiabatic system, we know that Q equals 0. There is no change in the heat. So from the formula, we can write that delta U equals negative W. So this is for an adiabatic system. Finally, an isolated system. In an isolated system, Q equals 0 and the amount of work done is also 0. So there is no work done, there is no interaction with any of the surroundings. So from this, we can say that delta U becomes equal to 0. We know that U is UF minus UI equals 0. So we can write that UF equals UI, which is the final internal energy is equal to the initial internal energy. Next, let's talk about a cyclic process. So a cyclic process is a thermodynamic process in which a system returns to the same conditions under which it started. So there are two examples mainly. One of them are heat engines and refrigerators. So the main principle of a cyclic state is to remember that the final and initial values of the internal energy are the same, and the change in internal energy is 0. So which means delta U net should be 0. So which gives you Q net equals to the W net. So let's start with a heat engine. So a heat engine generally uses heat to do work. So this is important to remember. So what happens inside a heat engine? So let's take a preliminary common understanding of a heat engine. So a heat engine takes heat and converts it into work. So this is the idea here. For that to work, it has to come from two sources. One, so whenever you have a heat transfer, so which means that it has to come from a hot source. So to get the work done, it cannot completely do the work. So it has to transfer some of the, so it cannot completely convert heat into work. So what will happen here is that the sum of the heat is released as waste. So we call that waste part a cold sink. So you have energy coming from a hot source that converts to work, and you have a cold sink. So why do we need a cold sink? Why can't heat can be converted into work? So heat is simply considered as a low grade energy, and work in simple sense is considered as a high grade energy. So you can convert high grade energy into low grade energy 100%, but you cannot convert a low grade energy into high grade energy 100%. This is the primary understanding of the second law of thermodynamics, which means that the total heat cannot be converted into total work. So most common heat engines, so the examples of heat engines would be, engines in your car. So car engines, more commonly called as the internal combustion engines. So or even a thermal power plant. So even a thermal power plant works on the same principle. So where it takes to convert steam, the heat from the steam, into mechanical work, which rotates the turbine to finally create electricity. So these are the common steps in a gasoline engine. So there is the first step. The first step involves the intake valve. So first step involves the spark plug. So what happens here is that once the fuel enters, it undergoes a compression. So that compression, so you have a fuel air mixture right here, that undergoes a compression. So under high compression, you have a spark plug that creates sparks. So the spark ignites the fuel. Now the fuel, once it ignites, becomes expanding gases. Now the gas tries to push the piston downward, so which causes the first rotation. And finally, the exhaust valve is opened, so which releases the exhaust outward. And finally back again, we open the inlet valve and let in the fuel air mixture again. So you have a compression, ignition, expansion and exhaust. And finally, you start back to fuel intake, which cycles the process over and over again to create the same effect right here. Now, let's look at refrigeration. Refrigeration works on the different principle of creating a heat change due to the amount of work done. So let's consider a small refrigerator. So how does the refrigerator work? So refrigeration works by taking work in, and what does it do here is it sucks heat from a body at lower temperature and pushes it outward at a higher temperature. So this is Q1 and this releases to Q2. So this here is the cold part and releases outward to the hot part. Now notice that without the work done here, bodies do not go from cold to hot. So to drive the energy transfer from a cold body to a hotter body, so it needs some work to be done. So that work internally can be simplified in the form of a refrigerator. So what do you have in a refrigerator? So first you have a condenser. So let's start with first one, the A part, which is the amount of heat that is taken in. Now notice that initially you have a compressor which attracts heat from inside the refrigerator and pushes that. So the attraction, the heat is taken by the evaporator, which is generally the refrigerant gas that is present inside your refrigerator. Now that gas takes in the gas and then it's gonna get compressed in the compressor. The compressor pushes that gas towards the condenser outside the refrigerator, and the outside the refrigerator you have heat coils which generally transfer the heat to the outside of the refrigerator and finally come back to the expansion valve, which again pushes the refrigerant material back into the compressor, the evaporator, which results in again creating the same effect. You have a complete cycle that is happening right here. You start from a low pressure liquid to a high pressure liquid and a low pressure gas, the gas becoming again high pressure gas and then high pressure gas, and once it evaporates, so the ones under condenser, it becomes a liquid back again. So you're basically turning the cycle over and over again until you achieve the temperature that you require. So next let's talk about section 3, the second law of thermodynamics. So we discussed the second law when we talked about the common sense of the heat engine. So recognize why the second law of thermodynamics requires two bodies at different temperatures for work to be done. Calculate the efficiency of a heat engine and relate the disorder of a system for its ability to do work or transfer heat as energy. Now, what does the second law of thermodynamics say? It basically states that there is no cyclic process that converts heat entirely into work is possible. So which means that you cannot convert all work into all heat. So this is basically saying that there is nothing that is 100% efficient in converting heat into work. So we basically say that the W net is equal to Q net, which is going to be QH minus QC. But the question here is that there needs to be a QC for that to work. So according to the second law of thermodynamics, the work can never be equal to the hot source in a cyclic process. So in other words, some energy must always be transferred as heat to the system surroundings for it to work. So with this comes the topic of efficiency. So efficiency is a measure of how well an engine operates by its is by so how well the engine operates. Now in general, efficiency is generally a measure of the energy, useful energy taken out of a process relative to the total energy that is put into the process. So the efficiency is basically output by input. So the output here is the amount of work done over the input here is the amount of heat that is transferred. So we know that the amount of net work done can be written as QH minus QC. So from this you can write QH minus QC by QH. So efficiency basically says that, so this when you further simplify, you can write it as 1 minus QC by QH. So the second law basically says that QC can never be equal to 0. QC is never equal to 0. QC must always be greater than 0. So for QC to be greater than 0, only then the efficiency is generally considered as a formula. So let's talk about an example. So find the efficiency of a gasoline engine that during one cycle receives 204 joules of energy from combustion and loses 153 joules as heat to the exhaust. So the amount of heat that is internally entering is 204 joules. The amount of exhaust is 153 joules. So we know the formula for efficiency is 1 minus 153 by 204. So now we have 1 minus 153 over 204, so which gives you a value of 0.25, so which when written in percentages can be written as 25%. So the efficiency of that engine is 25%. So this is how you can solve the problem. So next finally come to the topic of entropy. So in thermodynamics, generally a system is left to tend to go from a state where we have a very ordered set of energies to one where there is less order. So this disorder, the measure of a system's disorder or randomness, is called as the entropy of the system. The greater the entropy, the greater the system's disorder. So which means that the greater the probability of a disordered arrangement is likely to happen, then indicates that an ordered system is likely to become disordered. So putting simply, that an entropy of a system always tends to increase and it will never decrease. So the tendency of a system is always trying to increase the system right here. Now greater disorder means that there is less energy to do work. Now let's say if you have if all gas particles move towards the piston, all of the internal energy could be used to work. This is extremely well ordered system is highly improbable. That's the reason why we have a highly disordered system, which means you have average efficiency and high probable distribution of velocities. So because of the connection between a system's entropy and its ability to move to work, the direction of energy transfer becomes the second law of thermodynamics, which can be expressed in the terms of the entropy change, which says that the entropy of the universe increases in all natural processes. So the entropy of this universe is, the change in the entropy of the universe is always going to be greater than 0. So entropy can decrease for parts of the system, but it can be offset by a greater increase in the entropy elsewhere in the universe. So even if the system undergoes a decrease in entropy, so which means that for that decrease to occur, there must be increase somewhere else. So this is the idea behind the entropy of a system. So with that, we end our lecture on thermodynamics.